Section 11.7 is going to resurrect something that we talked about previously in section 11.4. If you remember in 11.4, we talked about tree diagrams, but before we talked about tree diagrams as a way to construct the entire sample space, all the possible outcomes, we talked about this thing called the counting principle. And so 11.7 starts off again with the counting principle, but we're going to take it in a slightly different direction this time. So again, just to refresh your memory, the counting principle says this. If you can do a first experiment and it has M distinct outcomes, so remember M is just a number, and then you do a second experiment and it has N distinct outcomes, again N is just a number, then when you do these two things together, it has M times N distinct outcomes. And when we were back in section 11.4, the first example I gave of this was what would happen if we flip a coin and then roll a die. You can write this down. You don't have to write this down. This is already in your notes from section 11.4. And back at the time when we did this, I asked this question. How many outcomes are there when I flip a coin? There's two, heads or tails. Great. Times, and this is what the counting principle says, how many outcomes are there when I roll a die? 6. So 2 times 6 tells me that there are 12 possible things that can happen. Okay, there are 12 combinations of results of my coin and results of my die. And then in that section, we used the tree diagram, we listed them out, we found some probabilities. But what we're going to do now is we're going to expand on the counting principle and we're going to see where that takes us. Okay, and it's going to take us somewhere fun for this section in our last section. So example 1. You need to make a 4-digit passcode for your phone. So you got an older version of an iPhone and it takes 4 characters. How many different passcodes are there? So why do we make passcodes? We're trying to keep our phone secure. We don't want people to be able to guess how to get into our phone. So let's see what happens. So we're making a 4-digit passcode. So if you're guessing, so if I hand you my phone and I say you're going to guess my passcode, how many choices are there for the first digit on my phone? 0 through 9, right? 0 through 9 is 10 digits. Okay, so you have 10 choices for the first digit. Then the second digit, when you make up your passcode, how many choices do you have for the second digit? 10. All right, good. I'm feeling a little more confident. How many choices are there for the third digit? 10. Yes, you're doing great. And then finally, how many choices are there for the last digit? Yeah, 10 each time. So 10 times 10 times 10 times 10. I pop that into my calculator, and that gives me that there are 10,000 options. Okay, so if you're still using your phone and you've got a 4-digit passcode, or if you're at the bank and you're using your ATM card, there are 10,000 different options that somebody would have to guess. So that makes it fairly unlikely that somebody is going to just grab your ATM and go to the ATM and pump it in unless they know something about you and can make a more accurate guess. But here's the problem. Computers, okay, computers operate much quicker than we do, so they can go through options. So a couple of years ago, you opened up your iPhone if you have one, and you were told, oh, now instead of a 4-digit code, you need to have a 6-digit code. So what I want you to do real quick, okay, take you just a couple seconds. Example 2, I want you to determine how many passcodes are possible, how many different options if you do a 6-digit code. If you have any questions about this, please ask them. But for each, I'm just going to ask this question 1 time instead of 6 times. For each of the digits, how many options do you have to choose from? 10. Okay, so first digit is 10. Second digit, there's 10 options. Third, fourth, fifth, sixth. So that means now, instead of 10,000 options, there are how many options for your passcode on your phone? 1 million. So it's even a little more secure. Okay, take a little longer to go through that. Okay, well, not every passcode. I mean, you've made passwords for websites and things like that. Not every password is just numbers. There's all sorts of different requirements, again, to keep them secure from computer programs that can guess these things a lot more quickly. So here's what we're gonna do. Example 3, you need to make a password consisting of 2 lowercase letters. I'm gonna underline lowercase and I'm gonna pause. If I ask you to pick a lowercase letter, how many options do you have? 26, yes, 26 lowercase letters. Again, I'm calling a timeout here because this is going to happen on your homework or maybe the test. If I don't restrict it to lowercase, if I say that case matters, so an uppercase is different than a lowercase, how many options are there now? 26 times 2, because a lowercase and an uppercase would be different, so it'd be 52 options now. Okay, so keeping that in mind. So whenever you go to a website and they say you need to have at least 1 uppercase and things like that, they're trying to make more options to keep things more secure. Okay, so you're going to do a password consisting of 2 lowercase letters followed by 4 digits. So how many possibilities are there? And now we're going to make some restrictions and things like that. This first one, no restrictions. So do this first one. You're allowed to repeat. Repetition of the letters and the digits is permitted. Just like I didn't mention it in the first 2 examples, but we're assuming in these 2 examples, repetition is permitted. Okay, that's why there was 10 options each time in those. So give the A problem your best shot. Remember, if you don't get it right off, we're here to learn. Okay, let's see how you did on this first one. You're going to get a bunch more tries to do this. Okay, so we're allowing repetition. There's no constraints here. So how many options do you have for the first of the 2 letters? There's 26 lowercase letters. Great. How many options do you have for the second letter? Again, 26. Okay, so that's my 2 letters. Now we have 4 digits. I'm just going to ask this once. How many options are there for each of my digits? 10. Okay, so 10 for the first, 10 for the second, 10 for the third, 10 for the fourth. Before we go to our calculators, does anyone have a question about where any of these numbers came from? It's legitimate to have a question. Okay, so if you do have one, don't think there's anything wrong with you. Okay, this is tough stuff to learn. So make sure you're getting what you need. When we do go to our calculator, what is the result? Okay, 6,760,000. Perfect. Yes, there we go. Lots of options. All right, well, we're just going to put some constraints on this now just to make sure you're getting the idea of the counting principle. So the B problem says, okay, still 2 letters, still 4 digits, but now we're not repeating. You can't reuse a letter or a digit. All right, how many options are there for my first letter? Yep. How many options are there for the second letter? Ah, yes, whatever letter I used here, I can't use again because we're not repeating. So that means now there's 25. Okay, now I go to numbers. I'm going to give you this. There's 10 options for the first number. How many options are there for the second? How many options for the third? And then for the fourth? Yes, I wanted to say 7 there for some reason. My brain was fixated. And then when you go ahead and multiply those together, what do you get? 3,000,000, if I'm heard right, 276,000. We good? Anyone not seeing where these numbers are coming from? All right, this next one's a little tougher. Okay, just because I want to make sure that you feel fun and challenged today. So same thing, 2 letters, then 4 numbers, but this time the first letter must be a vowel. And for our vowels, we're just going A, E, I, O, U, sometimes Y. Okay, we're not including W. Some people think W is a vowel. I disagree. Anyway, and then the first digit cannot be a 0, and then repetition is not permitted of any of them. Okay, so give it a try. This one's a little tougher. Challenge problem. All right, let's give this a try. Make sure you have clarity. So how many options do I have for my first letter? The first letter must be a vowel. A, E, I, O, U. Those are the 5 basic ones, but then I said sometimes Y. So that was what Miss White back in 1st grade taught me. So that's what, but if on the test, if I asked this and you did 5, I'd give it to you. Okay, so I'm going with 6 though. Okay, we're going all 6. All right, so now that's my vowels. Now remember, repetition is not permitted. So how many options do I have for my second letter? Only the first letter has to be a vowel. The other letter could be anything. Okay, so now I have 25 because I still can't repeat. So whatever vowel I picked here comes out of the pool of all the other letters. So I'm down to 25. Then I said the first digit cannot be 0. Okay, the first digit cannot be 0. So what is the number of options for my first digit? 9. Now for the second digit, I throw 0 back in, but I've already selected one I can't repeat. So how many options are there for the second digit? Again, 9, and then 8, and then 7. There you go. Challenge problem. That was difficult. And when we multiply those things together, what is 6 times 25 times 9 times 9 times 8 times 7? 680,400. If you used a 5 here because you didn't count the Y, then you have a little bit less. That's fine. I understand. The effort here is just to make sure we understand how the counting principle is working. All right, again, another example of the counting principle that's going to kind of take us where we want to be in this section. Example 4, you have framed pictures of six family members, and you want to hang them in the hallway in a nice row. And I want to know how many ways can we do that? Now, I'm just going to give you a little clarification. When I hang Grandma Marie's picture on the wall first, am I going to repeat Grandma Marie? No, she's done. Okay, so there's no repetition just because of the nature of the question. Okay, so that was something that my class on Thursday we had a little talk about. So I just want to make sure we're clear about that. Okay, how many ways are there to hang all 6 pictures on the wall? Okay, so how many options do you have for the first picture? Okay, and you hang that family member up, and then you move to the next. How many options for the next picture? Okay, and then I think we'd all say then there's 4, there's 3, then there's 2. When you get to the last one, there's only 1 option. Okay, so if I'm hanging all 6 pictures on the wall, it's 6 times 5 times 4 times 3 times 2. And what do I get when I multiply those together? 720. Great. Just real quick before we go and we define what we're talking about here and why this is significant. Let's say, I'm just going to do another example real quick. Let's say that I change that instead of 6 pictures. What if there's 8 pictures? Go ahead and just write that out for me, please. Just want to make sure we're clear on what's going on. Okay, if I have 8 pictures of family members now, I'm hanging them all in a row on my hallway wall. How many choices are there for the first? And then 7, 6, 5, 4, 3, 2, 1. And how many different arrangements of those pictures are there? 40,000, 320. Excellent. Great job. We still good? Everybody still tracking with me? So what we've got here is a specific use of the counting principle. Okay, this is a little different than making ATM codes like we were before. Now we have a number of objects and I want to know how many ways can I arrange them. So what this is called is a permutation. A permutation is an ordered arrangement. I don't think I spelled arrangement right, but I know you'll forgive me. A permutation is an ordered arrangement of a given set of objects. Order mattered to me when I was hanging the pictures on the wall, okay? Because it would have been a different arrangement if grandma was first versus if my sister was first, okay? That would be considered something completely different. When we come back in the last section of this unit, when we do that on Wednesday, we're going to talk about the difference if I have an arrangement of objects, but order doesn't matter, okay? If you're just concerned about a group of objects, not how they're arranged. But that's for Wednesday, getting a little ahead of myself. So what we did here with these pictures, these are ordered arrangement of objects. So the number of permutations of n distinct objects. So remember, this letter n, this is just a number, okay? So the number of permutations of n distinct objects is given by, well, notice what we did the first 2 times we did this. When we had 6 objects, it was 6 times 5 times 4 times 3 times 2 times 1. When we had 8 objects, it was 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. You just start at how many objects there are and you go through all the choices. So math people, because we're lazy, fundamentally, we don't like to write all those digits out. So we have a shorthand notation. When I want to do something like start with a number and then multiply by every next number down to 1, what this is called is a factorial. Okay, so this is called a factorial, and we would do it, this is how we would notate it. The number of permutations of n distinct objects is given by n with an exclamation point. Now that doesn't say to say n real loud, like n, I'm real excited, I got the answer. What this exclamation point stands for is factorial. Is what that's called. And what it means is whatever number n is, you start there and then you just multiply by all the whole numbers down till you get 1. Your calculator can do this. Okay, if you have a scientific calculator, you have an exclamation point on it somewhere. If you do not know where it is, when we do the next problem, I'm going to pause the video and then I'm going to come around and help you with your calculator. It'll take us 2 seconds to find it. Okay, so what I would like you to do then is do 2 things. 10 factorial. I would first like you to, just so that, because we're getting used to it, I would like you to list out what does 10 factorial mean? And then I'd like you to calculate it. And again, in case you don't understand, up here, 6 times 5 times 4 times 3 times 2 times 1, that would be, we could call that 6 factorial. And 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, that would be 8 factorial. So list out what 10 factorial is, use your calculator to calculate it. If you don't have a factorial, then you've got to punch in all the numbers, and I'm going to come around and help you find that on your calculator. Okay, so again, my calculator is not with me today. I got to get a new one. So 10 factorial, when you pop that in, well, first off, I asked you to do this. That's 10 times 9 times 8 times 7 times 6 times 5 times 4, 3. I'm exhausted now, times 2 times 1. You don't have to do that ever again. I just want to make sure you understood what a factorial was since I'm just mentioning it. But when you pop it into your calculator, what is that? 628,800. Excellent. Great job. All right. So what you're going to do for me now is just another problem. We're just getting used to this idea of the factorial and what a permutation is. So example 5, again, just a silly example, the simplest type. You've got 7 books. Okay. You want to decorate with them. So you're going to put them on a bookshelf. How many ways can you do that? So 7 books to put on a bookshelf. How many ways can you do that? Okay, so since I'm using all 7, then the answer to this question is 7 factorial. You can write down, there's 7 options for the first one, then 6 for the second, and 5 for the third, etc. But I'm just going to summarize 7 factorial. And what is 7 factorial? And I throw it into my calculator. One more. Example 6. Consider the letters A, B, C, D, and E. How many ways can all 5 letters be arranged if I'm just randomly writing letters down? How many different arrangements of those letters are there? I think you're on it. I'm just giving everybody else just a second to process it. I love the enthusiasm though. Thank you. Makes me feel good as a math instructor. Okay, again, I know there's just 5 objects here, so if you forget the factorial, it's totally fine. Okay, the factorial just helps when I've got larger strings of things. I don't have to write everything down. So if you just did this, there's 5 options for the first one and 4 for the second and 3 for the, and then 2 and 1. That's great. Okay, nothing wrong with that. Or if you wrote down this is 5 factorial, that's great too, because that's exactly what it is. And either way, when you put it in your calculator, how many options are there? 120. Okay, super duper. All right, so given that then, that's a permutation. Permutation is an ordered arrangement of objects, and what we've been doing is using all of them, right? We had 6 pictures of family members, we used all of them. We had 7 books, we used all of them. We had 5 letters, we used all of them. So now we're gonna take it to the next level and we say, okay, now what happens if I don't want to use all of them? What if I want the ordered arrangement and I just use some subset of them? So example 7 says, for the previous example, how many arrangements are possible if I use 3 letters? Well, it's just the counting principle. How many options are there for the first letter? 5. How many options are there for the second letter? And then finally for the third letter. Okay, this is where we started our time. So that is, there are 60 options. Now, there is a quick, clean formula for this. And there's a button on your calculator. So if you have the exclamation point on your calculator, this button is going to be in the same place, more or less. This is called the permutation formula. Okay, it works no matter how many objects you're using, but here's the essence of this. The number of permutations, meaning the number of ordered arrangements that are possible when R, again, that's just R is just a number, when R objects are selected from a total of N, is given by the following formula. Okay, so the example that was on the bottom of the previous page, I was choosing 3 of the letters out of the 5 letters. Okay. 3 out of 5. So here we're choosing R objects out of the N objects. And here's how this formula looks. Capital P. P stands for permutation. Okay, that's what you write down when you have your ordered arrangement. You know order matters. And then on this side, this number is going to be N. So I'm notating for you so that you know what everything stands for. N is the total number of objects. And we're choosing R of them. Okay, so on this side, this is how many I'm choosing. So on your calculator, if you have a scientific calculator, there's a button that says that right there. P with an N on the left subscript and an R on the right subscript. And here's the formula, okay? And you need to know this formula. I'm going to show you exactly what my expectation on the test is going to be in just a moment. In the numerator of this is N factorial. And what N factorial is that's the permutations of all the objects. We just saw that. That was what we were doing at the bottom of the previous page. So this is the permutations of all the objects. And in the denominator, what we're going to do is we're gonna divide by the number of permutations of the objects I'm not using. So if I have N objects total and I'm grabbing a group of R of them, that means the ones that are left over, there are N minus R left over. So in my previous example, we had 5 letters, we were choosing 3 of them. That means how many were left over? 2. 5 minus 3 is 2. That's just the formula version of what we just did. Okay, so we're going to work this next example together because I want to show you what my expectations are, what I expect you to know, and to show me that you know on the test. Okay, when you're in my math lab, just give the answer whatever my math lab is asking for. Okay, but so just keep this in mind. Example 8. You are among 9 people forming an astronomy club because astronomy is awesome. As a group, you decide to put each person's name in a hat and randomly select a president, a vice president, and a secretary, because what better way to pick leadership than randomly, right? So how many different arrangements of our officers are possible? Well, just as an aside, before we do the problem, when you go through your homework tonight, okay, everything in this section is a permutation, meaning order matters. So one thing I want you to ask yourself for each problem is, why does order matter? What about this problem is communicating that order is important? So for this particular problem, we've got 9 people. We're choosing a president, a vice president, and a secretary. What about that tells you order is important? There's a ranking. There's a hierarchy. If you get picked first, it's different than you're going to get a different position than if you get picked third, right? Okay, so that's why order is important. Anytime there is an inherent ranking or hierarchy or something like that, that indicates order. Okay, so in this one, you would say the order is important because there's different positions. All right, well, let's do this. Here's what I expect from you on the test. The first thing I expect for you is say, okay, you need to identify that it's a permutation. So you're going to write a P, as opposed to when we come back next time and order's not important. That's something completely different. How many total objects do I have? 9. And how many objects am I choosing? Okay, 3. I know the objects are people, but we're just mathematically, we're just calling them objects. Okay, so I have the permutations of 9 objects and I'm choosing them 3 at a time. The second thing I want you to show me, okay, so that's the first thing. What that tells me is you know that order is important. It's a permutation, okay, so you're communicating something to me. That's why I require it. The second thing you're going to show me is this. Okay, well, if I have 9 objects, that means there'd be 9 factorial arrangements if I used all 9. So if we had 9 positions and we were putting everybody in, that would be the arrangements. But we're not. We're only choosing 3. So that means how many people are going to be left over? 6. So that's 9 minus 3 factorial or 6 factorial. So you got to show me one of these two things. This just shows me that you understand what's going on with my permutations. Now at this point, if you have a calculator that does permutations, use it. Okay, and if you don't know how to use it when we're doing the next example, just call me and I will come right over. If you do not have a calculator that does permutations, here is the longhand method to do it. Okay, so here's what you would do. My 9 factorial, what I'm going to do is I'm going to unstring this a little bit. And I'm going to write that as 9 times 8 times 7. And then 6, 5, 4, 3, 2, 1, that's 6 factorial. And the reason that I'm stopping with the 6 factorial is because I have the same thing in the denominator and it'll just cancel now. 6 factorial cancels with the 6 factorial. And 9 times 8 times 7, or whatever your calculator tells you, you should get 504. So if you got something different when you put the permutation in your calculator or you do not know how to do that, let's talk about that. In the meantime, example 9, I would like you to do example 9. Okay, so here's the first thing you're going to show me. So this is required. So on your paper, you should have this thing written first, a P, with how many total objects do I have? I have 16 total objects. Yes, how many at a time am I choosing? 5. Now, why does order matter in this problem? Why is it a permutation problem? It's a leaderboard. Yeah, it's a leaderboard. So it matters if you're first or second or third or fourth. Okay, so that's why order matters. Okay, there's a ranking that indicates it. Okay, fantastic. Here's the second thing you're going to show me. I've got 16 total objects. So if I used all 16, that would be the number of permutations, 16 factorial. But I'm not using all 16. I'm leaving out 11 or 16 minus 5 factorial. Okay, again, that's done. And when you pop that into your calculator, what is the number of permutations of 16 objects if I use 5 of them? I'm sorry? 16 minus 5, that is 11. What does this, so 16 factorial divided by 11 factorial, great. What does this turn out to be? How many arrangements are there? 524. 160. Yes, if you don't know how to get that on your calculator, let's talk, because it's a real easy thing. Okay, you just might not know the keystrokes, and that's okay. In the meantime, do example 10. Again, identify why an order is important on this, and then do the problem. And then we've got one more little thing to do, and we'll be done talking about permutations. Okay, so I've got a bicycle club. They got 10 different routes. The members want to ride. There are 6 dates to fill for trips. How many ways can the different routes be assigned to available dates? So why is order important on this one? Yeah, because there's different dates. So where I'm going on March 1st can be different. Okay, so order is important. I'm not just picking there, it's not saying there's 10 different routes and they just want to pick 6 of them to go to. Okay, if there's no ranking, if there was no hierarchy, if there was no order like dates, then that would be something different. If I'm just saying I want to pick 6 of them and then we're going to go to those. This one we're assigning to specific dates. That's why order is important. All right, so it's a permutation problem. Order is important on this one. I have 10 objects. I'm choosing 6 of them. So that is 10 factorial. That would be the arrangements if I was going to all 10, but I'm not. I'm only going to 6. So that means we have to leave 4 off. So you either wrote this or you're writing this. In either event, when you pop that into your calculator, how many different arrangements are there for bicycle trips? Perfect. 151,200 different bicycle trips that we could plan. Okay, excellent. Counting principle. So now we're going to end up with this last situation. Okay, again, there's lots more detail we could go into, but this is enough for us with a very nice surface level treatment of permutations. So now example 11, the difference here is this. I'm going to use all the letters. We're going back to the situation where I'm using all my objects. But the thing is, in this word right here, some of the letters are repeated. At the example on the bottom of the first page, we had A, B, C, D, E. There are 5 different letters. And so what happens is if I'm arranging my letters, it doesn't matter which N I pick, they all look the same, right? So it doesn't matter if this one would be in the position or this one, it's all the letter N. Okay, so how do we account for if I have duplicates of objects? Okay, so how do we account for the situation where I have duplicate objects? And that hasn't happened to us yet. We were assuming that the bicycle club, it said they had 10 different routes. The skiing event, we're assuming there's 16 different people. The people in the astronomy club, there's 9 different people. So this hasn't occurred to us yet. We've got duplicate items. So we're not going to talk about the situation where I just pick a few of them. We're going to keep it as relatively simple as possible. We're going to use all the letters. How many ways are there to do this? Okay, well, great question. So first off, I'm going to do example 11, then you're going to do example 12. How many letters are in the word Cincinnati? Okay, there are 10. So the top is going to be 10 factorial, just like before. And again, 10 factorial, this is the ordered arrangement of all the letters. It's the ordered arrangement of all letters if they were different. I'm going to put that in parentheses, if they were different. I didn't do a good job leaving myself room, so I'm going to scribble out the 10 factorial and I'm going to move it over here. Sorry, I don't mean to be messy. Okay, so the 10 factorial is the ordered arrangement if I use all 10 different letters, but I don't have 10 different letters. I've got repetition. So what I have to do is I have to divide by the arrangements of the duplicates. So first, I've got N's. I have, in this case, 3 N's. So I'm going to divide by 3 factorial. And I'm going to put underneath it the letter N. You don't have to do that. I'm just doing that for your notes later. This is the ordered arrangement of the 3 N's. So we're dividing by that. What other letter repeats in Cincinnati? How many C's are there? Okay, so 2 factorial. There's 2 C's. Great. Is there anything else that repeats? The I does. There are 3 I's. So 3 factorial. Now, unfortunately, unless you have a statistics specific calculator, your calculator probably does not have the ability to do this. So we are going to have to do this the longhand method. So what I'm going to do in the top is I'm going to do 10 factorial. I'm going to stop it at 3, 2, 1. I'm just going to write 3 factorial. So what I mean by that is this. I've got 10 times 9 times 8 times 7 times 6 times 5 times 4, and then 3 times 2 times 1 is 3 factorial. In the denominator, this 3 factorial that's right above the I, I'm just going to leave it as 3 factorial. It's going to cancel. So I'm going to put 3 factorial right there. The other ones, though, I'm going to expand. 2 factorial is 2 times 1, and 3 factorial is 3 times 2 times 1. And when you do this, if you do everything right, you should not have any denominator left. Everything in the denominator should cancel with something in the numerator. You should get a whole number answer. Okay, so if you get a decimal or a fraction, go back to the drawing board. You've just lost track of something. So here, the 3 factorial deletes or cancels with the 3 factorial. I'm going to cancel this 2. 2 goes into 4 and leaves 2. 3 times 2 here is 6. I'm going to cancel this 3 times 2 with the 6 that's in the top. So 3 times 2 is 6 is going to cancel with the 6 in the top. And now I've gotten rid of everything in the denominator. It's just a matter of multiplying. And when I do that, I have 10 times 9 times 8 times 7 times 5 times 2. So 10 times 9 times 8 times 7 times 5 times 2 turns out to be 50,400 different arrangements. All right, so your last new problem of the day, before I ask you if there's any questions from your homework you've had so far, is to do the same thing with example 12. Determine the number of ways you can arrange the letters in Mississippi. All right, so let's see how you did. If you got any questions, any question will be reasonable. This is difficult stuff. So how many letters are there in the word Mississippi? 11. So if all the letters were different, we'd be done. Okay, there'd be 11 factorial ways we could arrange all the letters in Mississippi. But I have duplicates. So what repeats in this word? Okay, I heard S's and I's. Yes, both to yes. So there are 4 I's. And there are 4 S's. And there's 2 P's. Does anything else repeat? Okay. All right, then probably the hardest part, hopefully, is just being able to evaluate this. So I'm going to expand the 11 factorial. So 11 factorial is 11 times 10 times 9 times 8 times 7 times 6 times 5. And then the 4 times 3 times 2 times 1 will remain 4 factorial. And the reason I did that is because I have these 4 factorials. I'm just going to leave the first one. We'll cancel that. Then this 4 factorial is 4 times 3 times 2 times 1. And then 2 factorial is 2 times 1. So remember, 4 factorial is not 4. I can't just cancel 4 factorial. Like I can't cancel this 4 right here with 4 factorial. Those are different things. Okay, that exclamation point has meaning. So I can only cancel a 4 factorial with another 4 factorial. And then the rest of the numbers, I'm just going to find ways to cancel them out. So 2 goes into 6 and leaves 3. This 2 goes into 8 and leaves 4. 3 goes into 3. I'm going to cancel both those 3s. And then 4 goes into 4. Great. That makes things nice and relaxed. So the answer to this is going to be 11 times 10 times 9 times 7 times 5. And what do we get when we do that? $34,650 sounds delightful to me. All right, so let me pause. Let me stop the recording.